Okay, so welcome to the continuation of lecture 13. We've been looking at limit cycles, just doing the introduction, and I said it was an isolated closed orbit that either retracts or repels corresponding orbits, sort of nearby orbits in a limited region around it. It can appear in any dimension, but we're focusing on limit cycles in 2 dimensions. And then I said it's quite an expensive exercise to look for limit cycles, so the first thing we wanted to do was look and try and classify all systems in which they do not occur. So we're busy proving the non-existence of limit cycles. Okay, and then the first method I said was basically the idea, if you have a gradient system, in other words, x dot is equals to the gradient of something. So you're going to have that, you basically have, if you have x, the vector is equals to x, y, you're going to have x dot equals to minus dv dx, and you're going to have y dot equals to minus dv dy. Okay, and if that is true, then there are no limits. There are no limit cycles in the system. And remember, I said, how do you know if you're given a system x dot equals to f of x comma y, and y dot equals to g of x comma y, that it's a system like this? Okay. If you're just given these, how do you know you can write it in that form? And I said there was one trick that you could do. You could work out the curl of this vector. If that is 0, then it's the case. Okay? A quicker way of seeing that is to note that if this thing is a potential and you take dy of this thing and you take ddx of this one below, then they must be equal. So that's another check. It's equivalent. In fact, in 2 dimensions, those checks are equivalent. The check where I said you take a curl is true in general, it's because you can find gradient systems in general, but just for 2 dimensions, if you were to take df dy, and that were to be equals to dg dx, right? Which is obvious if this is true, then this thing is a gradient system. Okay, so this provides a very quick check for whether or not you have a gradient system. And then we went through this proof over here, and we said that it's a gradient system. You can prove that there's no closed orbits. It was a proof by contradiction. And I said, this is great. We can definitely always, if we get a system, we can do that check. And if it works out, then it's a gradient system and we're done. But very few systems are actually gradient systems. Okay, and so we want a general thing, a more general thing. Just another comment, if you have a gradient system, okay, you basically have the case where your actual trajectories are all going to flow downhill to the fixed points. So it is exactly the opposite of a conservative system where our trajectories were flowing around contours. It's just to put it in context. Anyway, so what we want to do now is to get another more general check that goes beyond systems that are a gradient system. And what we do to be able to do that is the idea of Lyapunov functions. So this is sort of a generalization of the idea of a gradient system, but it's more powerful. So the idea of a Lyapunov function is, suppose you have a system x dot equals to f of x, okay, and you have a fixed point at x star, okay, and now you're going to say if there exists a Lyapunov function, okay, so it's no longer directly associated with the differential equation, it's just another potential function that exists. if there exists a Lyapunov function which is continuously differentiable C infinity, in other words, a smooth function, and it's positive definite, so it's positive everywhere, such that basically V of x is greater than x everywhere around the fixed point, and V at the fixed point is 0, okay? And you can prove that as you move along a trajectory, V dot is less than 0, okay, for all x not equals to x star, so that all the trajectories run downhill, okay, then x is globally asymptotically stable. Okay, you can think we've already, oh, this is horrible, we've already had such a system when we looked at the damping of the pendulum, right? Remember when we had the pendulum, we had a second order equation, we had the potential, that was that double well potential. It was positive everywhere except at the fixed points, and then we basically argued that the pendulum would eventually go down and get stuck at the 0 fixed point. And this is exactly the same thing, except it's a more general argument. Okay, so the pendulum that we had is an example of that. So the moment you have a system and you have an additional potential that has these properties, you can prove that this fixed point is globally asymptotically stable. And the idea is basically that using these conditions, you have your potential here. This condition, it's a positive potential, so it's like a cup. The V dot is less than 0 along all the trajectories, basically means that at every point along a trajectory, it's going to run downhill, okay? And if it does that, you can basically show it will always run to the minimum of the potential, which is where V star is equals to 0. Okay, so it's a very nice intuitive check. It's more powerful because you no longer require this thing to be a gradient system. Okay, if in fact this thing is a gradient system, which is the example, then you can just choose V to be the potential itself. Okay, or you can basically choose this V of x to be that V of x. So this Lyapunov functions includes everything we've looked at previously, but it is more general. Okay. So basically, all initial conditions go to the fixed point, which is stable. Okay, so now let's take, for an example, do closed orbits exist for this system? What would you do? You could. Yeah. I mean, you would at least find your fixed points. So you would do the linear analysis. You would be able to tell whether the fixed points are stable or unstable. But that would not tell you whether you have a closed orbit.
If I find a linear center?
That would still not tell you whether you have a closed orbit. Remember, a limit cycle is an isolated closed orbit, so linear center is not a limit cycle. Generally, things that have linear centers you can perturb into a limit cycle. Okay, they become it if you change the parameters, but they are not. It's not proof. So the first thing I would do here is, yes, do the linear analysis, get an idea of where all the fixed points are, because that's at least the potential places where the thing can go. But after that, I would first check whether I have a potential system. Okay, and how do I check that? I take the y derivative of x, so that's 4, and I take the x derivative of g, which is -1, and those aren't equal, so I don't have a potential system. Okay, that's the check. So if that check passed, then you could say you have no closed orbits. And the next thing I could do is, if I was being kind, I could suggest a trial Lyapunov function, which you then could go and check whether it has the properties of the theorem. And in this case, I would say, suppose you had a trial Lyapunov function like this. I haven't given you the whole function. I say it's basically x squared plus ay squared. The reason I have the squares, remember, is that I want my Lyapunov function to be positive definite. So it has to be greater than 0 everywhere except at the fixed point. So here comes your linear analysis. The fixed point you get when x is equals to minus y cubic. You put it in there, and so you have y cubic plus 4y must be equals to 0. So one fixed point occurs at y equals to 0, and that's it. Okay, so y equals to 0, x equals to 0 is a fixed point. So we know that at the fixed point, this Lyapunov function is 0, which is the other condition that we had. We know it's positive definite, provided a is positive. Okay, and what we're going to do now is we're going to choose a so that this thing decreases along the trajectories. So the problem always with the Lyapunov function proof is that you have to find the Lyapunov function. Okay, and usually you guess things with positive powers and positive coefficients in front here, but you have to find it. Okay, so I'm not going to, it's not something I'm generally going to give you in a test. I'm going to give you an estimate of what the thing is, but if you're working in practice, guessing these things is sometimes quite hard. You get a feeling that they should exist and you need them for the proof, but you have to guess them. Okay, so A is a parameter to be chosen, and so what do we do? The second property of the Lyapunov function is that V dot has to decrease along a trajectory. So we then compute V dot, and V dot is equals to 2x times x dot plus 2ay times y dot, okay, just from differentiating this thing using the chain rule, and then we're going to substitute what x dot and y dot is into these. Okay, so it gets quite involved. You get something like this. You multiply it out, okay, basically by grouping like x and y terms together, and this thing has to be less than 0 for all possible x's and y's. Okay, and we've got to pick a that it's so. So this term is easy, it's less than 0. That term is easy, it's also less than 0. This term is sometimes not, right? So x can be positive or negative while y is positive, or if x is positive, y can be positive or negative. So we want to set this term to 0 to ensure that the whole thing remains negative. And so the natural way to choose a is simply to say choose a equals to 4. And then you have that v dot is simply equals to minus 4x squared minus 8y to the 4th, and that's always negative. Okay, so then v dot is this, and it is always negative for all xy that's not at the origin. Okay, so it's clever. You have a lot of freedom to choose your Lyapunov function. I mean, you didn't have to just choose this thing. You could have put plus y to the plus a times, say, b times y to the 4th as well. That would have been a fine Lyapunov function. Yes?
So I can try different polynomials.
You can try different. Generally, what works here is you try different polynomials with positive even powers. But you don't even have to choose just x squared plus and y squared. You can, for example, choose x minus 3y, the whole thing squared. That will also work. Okay, so there's quite a lot of choice in what you can choose. But typically, yes, for Lyapunov functions, you choose positive polynomials or polynomials with even powers. And then you choose the coefficients in front of them so that you have this property that you require for the proof. Okay. So that's enough, the fact that you've satisfied that v is positive definite, v dot is less than 0 along the trajectories, and that v is 0 at the fixed point is sufficient for the proof to be applied. So you have no closed orbits in this case. Okay, if it had been a gradient system, it would have been much easier. You just had to do that check below, For this one, you have to do more work. Okay, this idea of Lyapunov function is used a lot. Okay, it's a very, very useful tool in various ways. And you'll see it'll come back in higher dimensions as well. If we try and prove that the trajectories go to a certain fixed point. Okay, so all the trajectories approach the origin, and that's that. Okay, so another one that is used less often, but it can be used places where you don't always have a Lyapunov function, is a thing that they call Deluxe Criterion. Okay, I'm just going to give it to you for completeness. I haven't found many places to apply it because I usually try and find a Lyapunov function. That's my thing. You know, I check this quickly, which doesn't often happen to be satisfied, and then I look for a Lyapunov function. Okay, so Deluxe Criterion is slightly more complicated to apply. It goes as following. Okay, we have the differential equation x dot equals to f of x. It's a continuously differentiable vector field on a subset R. Okay, so we're basically just requiring that f and g are continuously differentiable on a region R over here. We're also going to say, once again, we're going to say if there exists g of x in R that is continuous, that is C infinity, then we're going to say certain properties. Once again, we have not told you how to get g of x. That's the problem with differential equations. Some part of it isn't a recipe. Some part of it comes from insight and practice. And people that are really, really good at it get very beautiful results, but it does take a certain amount of artistry to get these things. Okay. So if there exists a g that is C infinity such that the divergence of g times x dot has one sign throughout R, you can see it's a completely different kind of test. Okay, so what you're basically going to do is you're going to take this vector field, you're going to multiply it by g, and then you're going to take the divergence out of there, so you're going to get a scalar. Okay. If that thing has one sign throughout R, then there is no complete closed orbit in R. And the proof is nice because it's subtle and it's a little bit different from the things we've been doing up until now. Okay, so the proof is once again by contradiction. So the proof goes, suppose there exists a closed orbit, okay, and we're going to call that orbit C in R. So what we have is, we have this closed orbit, we call it C, okay, it lies entirely inside of R, and that's an assumption that it exists. And we're going to say, let A be the region inside of C, so it's this light colored region, okay, and N is the normal that points outward, okay, so the normal points outward of A, it's orthogonal to the tangent of this trajectory, okay, by definition of what normal is. And dl is a line element, so dl along this trajectory. Okay, so you basically have dl pointing like infinitesimally along this x dot. In fact, dl and x dot are proportional to each other. Okay, then you have a thing called Green's theorem, which you should have encountered. You have encountered it. Okay, it basically connects the area to the boundary in 2 dimensions. So Green's theorem basically goes, the divergence of a function integrated over the area is equals to basically the flux of the function leaving the boundary. Okay, so written here we basically have the divergence of the function which we're considering is g of x dot times dA is equals to the line integral along C of g times x dot dotted with a normal of dl. Okay, a physical way of thinking about it is basically the way in which the function moves apart inside is equal to the flux of the boundary. That's how physicists use it, but it's this rigorous Green's theorem. Okay, and so we're going to use this now to actually prove that having a trajectory is impossible. And the way we prove it is by the assumption that we've made on g of x, right? So we assumed that the divergence of g of x, it's one of our assumptions, has one sign throughout R. So in particular, it's going to have one sign over all of little a, or all of the light-colored region, which is contained inside of R. Okay, so so it has one sign. So we know that this thing is non-zero because the integral of something that has one sign over an area is either a positive or a negative number. So that's all we need, it's non-zero. However, this thing is 0. Okay, and it's 0 because x dot is always tangent to this curve, dl, and n is also always orthogonal to the curve at every single point. So at every single point, x dot n is equals to 0. So there we have the contradiction. So C cannot exist. Okay, it's a cute proof. I've very seldom used it. Somebody must have invented, I don't know the history of it, but somebody must have invented it because he couldn't find a Lyapunov function and thought about the problem differently. No, I'm serious, because he must have had a problem that he had to prove something. And he's, I don't know, something pushed him and he came up with this, which is kind of nice. So this is basically the 3 checks that you have to prove that limit cycles do not exist. Right. But if you can either carry out the checks or you can follow your intuition that they do exist and try and find them. But if you want a definitive answer, sometimes these guys are useful. And in fact, people that have tried to eliminate limit cycles from certain things have actually used them, and you can get some powerful results that way. Okay, so what we now want to do is, now that we've got all the checks for limit cycles that don't exist, we want, like something, to find the conditions for limit cycles to exist. And we would like to find a theorem that predicts that. And possibly the most famous theorem for doing that in 2 dimensions, or the most famous theorem for 2 dimensions, is the Poincare-Bendixson theorem. And you'll be using this a lot because it gives you the criterion for actually proving that there's a limit cycle in a certain region. So it's known as Poincare-Bendixson theorem. Poincare, the 3-body problem, the guy that proved that chaos existed the first time, it's after him. So this theorem is very old. It's also very influential, but it's got a catch. It's only valid in 2 dimensions. Okay, so you can only apply it in the 2-dimensional case. It fails, and there are other things possible in 3 dimensions. Remember, in 2 dimensions, chaos never occurs. It cannot. It's stopped by the fact that you can only move in 2 dimensions and you cannot cross orbits. In fact, this Poincare-Bendixson uses that. When you go to higher dimensions, then it is no longer valid. So when you're applying it, only apply it in 2 dimensions. Okay, so it goes as follows. Suppose R is a closed bounded region in R2. Okay, so any random region in R2. Suppose further x dot is continuously differentiable. In other words, there are no jumps in it, so it behaves predictably. And then it's continuously differential basically in an open set containing R, so a little bit around R, so it actually is just off the boundary. It's also continuously differentiable. And suppose f has no fixed points in R. Okay, so that, suppose for example there was a fixed point in here, so over there, then you could define a new region and you could cut out that fixed point and put the boundary just a little bit around the fixed point and you'd still have a valid R. Okay, so no fixed points in the region R that you're considering. Okay, but you are allowed to cut things out and then redefine your region. And now the next where it gets interesting is, suppose you can show there exists a trapped trajectory T in R. Okay, and by trapped, I basically mean you have a trajectory T that is in R for some time T0, so it starts in R, and you know that it stays in R for all T greater than T0. Okay, so whatever this trajectory does, it doesn't escape this region, this closed region. So it stays in there. In other words, it never goes across this line or it never goes out of that line. It just stays stuck in this region. If those four things are true, then you can say that either T is closed, in other words, the trajectory you're looking for, or it is going to spiral towards a closed direct trajectory. In other words, this T is going to go around and eventually it's going to approach this closed trajectory. Okay, so this is basically the proof for an attractive limit cycle inside the region R, or the theorem. So basically, either way, there exists a closed trajectory in R. This theorem is very, very powerful, and intuitively it's very, I'm not going to do the proof, but intuitively it's easy to see. In other words, it basically it results from the fact, remember you have a theorem that your trajectories exist, the solutions to this problem exist and are unique, and that implies that in 2 dimensions they never cross each other. And that's enough to actually say you have this trajectory T, okay, there are no fixed points, so it can't go to a fixed point, it's got to go somewhere. It cannot, in other words, so the T can never go out of the thing because you know by assumption that it's stuck inside. It can never go in here, so it has got to approach something that moves around like that. That's its only option. It can never cross this thing if you have an orbit like that and go out. Okay, so this Poincare-Bendixson theorem is basically the criterion you need in 2 dimensions to prove that there is an existent thing. Okay, so what typically happens now when you try and apply this theorem, okay, the thing that's hard to prove is this fourth part, okay, because it's easy to find a closed bound region in R2, you just draw one. You just check that this thing is continuously differentiable. You identify all your fixed points and you cut them out. That's a fine region. But what is difficult is to prove that in this region there's a trapped trajectory in the region R. Okay, and so what we typically do, and that I'll give you examples of the next time, is the art is then to choose this region R so that on the boundary of R, all the arrows, the phase space arrows, always point inward. So they're all going to point inward in this direction, and they're all going to point outward around these fixed points. Okay, so if you can find a region R that has that property, that on its boundary it obeys the fact that the x dot decreases along the boundary or over the boundary, then you're fine. Okay, and constructing those regions is the art form. Okay, so we'll look at several examples of doing that. One way, if you know the problem is close to something that has almost spherical contours, like for example the case with the pendulum that was going round, you know that if you picked one of those contours, you proved, in fact you chose a good region of R. You basically proved that all the trajectories would go across that contour once you got into that region that inside the saddle. So you would pick a no, that won't work. Okay, I'm talking nonsense. The pendulum would never have a limit cycle because we proved that with the Lyapunov function. Okay, so the pendulum would never have a limit cycle. But suppose you had another thing, that you had a place where you could pick a sphere in phase space and you proved that all the arrows would go over. Then it would go into a region, then you have a possibility either it goes to a fixed point or it goes to a limit cycle. Then you identify all the fixed points, you cut them out, and see if you can, if it's an unstable fixed point, then the arrows would point out and then you would have another region. Okay, so I'll look at specific examples of doing this the next time. Right, I'm going to stop there now and then have a look at make some comments about the test.